All right, our final topic on information theory is Kullback-Leibler divergence, which we're just going to touch on so you're aware of what it means. So this Kullback-Leibler divergence, or KL divergence to make it less of a mouthful for me, enables us to quantify the relative Shannon or differential entropy of two different probability distributions that are over the same random variable. For example, if we have one probability distribution that's described by px, and then another one by qx, so we have the same random variable x in both cases, but two different probability distributions, we can compare them with KL divergence, which is denoted as KL, and then here we're saying that we're comparing p and q, and so we have the expectation of the log p, the log p-value, minus the log of the other probability that's given by q. You can see this is closely related to the self-information formula that we've already been talking about. We're simply comparing self-information. And a concept that is derived from this comparison, from this KL divergence, is called cross-entropy. So all of the detail of cross-entropy and how we derive it from KL divergence is beyond the scope of what we're covering in these probability and statistics live lessons, but I wanted you to be aware of it so you could dig into it more on your own time. And I also wanted to mention its relationship to the cross-entropy cost function, which is a very important function in neural networks, in deep learning. In fact, it's ubiquitous. It's the cost function of choice whenever we have a neural network, a deep learning network, that is predicting discrete categorical outcomes. For example, for a binary classifier, so a model that predicts whether a set of inputs corresponds to a binary outcome, so, is this image a hot dog or not a hot dog? Is this movie review a positive review or not a positive review? So whenever we have a model that's acting as a binary classifier like that, we would use cross-entropy cost, which is given by this equation here. We have those natural logarithms that we see in self-information and in the differential and Shannon entropy that we talked about earlier. So the exact derivation of this equation, as I said, is beyond the scope of what we're covering here. It would just take too long, and I don't think it's that important for you to be a great machine learning practitioner or data scientist. So I am simply showing you what the equation is and encoding it in Python code here. So we've got our cross-entropy method. Lots of deep learning libraries come with their own built-in, but I wanted to show you what it involves. So in this case, y is the true known output, the correct output that we're trying to learn with our classifier. So it could be a value indicating this is a positive movie review or this is a negative movie review. And then a is y hat, our model's estimate of whether the inputs correspond to a positive outcome y or a negative outcome y. So a could be any value ranging from 0 up to 1, where if y is 1, so let's say y is indicating that this is a positive movie review, if our model estimates a value very close to 1, say 0.9997, then the cross-entropy is very small, very close to 0. So our cross-entropy is low when our model guesses or predicts, I guess it isn't totally guessing in a lot of cases, when it's trying to predict based on some inputs. If that prediction is close to the desired output of our binary classifier, then the cross-entropy is low. As our model gets outputs, as it predicts outputs, y hat values that are further away from the correct value. So if it is a positive movie review and our model provides a y hat of 0.9, well, that's not as confident a model prediction. And so our cross-entropy goes up a bit to 0.1. And same thing, as we get further and further from that 1, our cross-entropy gets larger and larger. Right, so if you want to see cross-entropy in action in a neural network and see more examples of how it works and why we use it, then you can check out my deep learning live lessons or my book, Deep Learning Illustrated.